Hi, I'm just going to do a quick recap before we start today's lesson. So we're in the end, basically, of the topic of completing the square. We introduced it and we said Babylonians, when they used to do it, did it geometrically, and they basically turned a rectangle into a square, just with this missing part. We see that we have to halve whatever's in front of the x, because then we sort of move it down, we make the square, we just then need to minus that thing squared every single time. It doesn't matter if it's negative. We did some other examples, and we had an immediate application of finding a turning point to the quadratic, a maximum or a minimum. We generalized. Then we looked at the case when you have a constant in there as well, and there's just an extra little, we just basically ignore the constant, put it back in at the end. Did some more questions, including ones where we might be given a turning point and get back to the quadratic doing the opposite process. So that was a good start, and then we sketched some graphs. We've done a lot of sketching of graphs. Next, I just recapped it and looked then at quadratics that we have a number in front of the x squared other than 1. And this was a bit trickier. We had an extra step. And actually, if I just jump to the lesson that we did, you can see we factorized the 2 out, and then we completed the square on the thing inside of the bracket. We didn't worry about factorizing out the 1, because you just end up putting it back in at the end anyway, so it just makes sense to leave it outside. Again, we found the turning point. We did it for things like 3. Numbers went towards it nicely. We then looked at some negatives. You have to be a bit more careful here. You get sad quadratics. We even looked at some where you get fractions going on, and an exam sort of question before finally going for the general quadratic and completing the square on that to get a general formula for a turning point. This is where we begin today's lesson. So just to test you on a few of these things, can you have a go at the following questions? Pause the video, try them out, and I'm going to go through them. So first one, it's going to be x, but you need to show enough working. I don't start by expanding any of these and trying to go back. Try and do it by completing the square. So it's going to be x plus 4 squared minus 16 plus 2, and that's enough. We can see that the answer is going to be A. Bringing back in straight away a number in front of the x squared other than 1, so 2x squared. Can you try this one? So if you remember, we took the 2 out. It's going to become 6x. Leave the 5 alone. And now square bracket and complete the square on x squared minus 6x, so x minus 3 squared minus 9. Expand the bracket out, there's a few steps. It's going to be minus 18 plus 5, which will give us minus 13. So it's going to be D. And just one with a negative in. I'm going to take a minus out. It's going to become x squared minus 2x. I've sort of rearranged it as I've gone along. Still plus 15. Now factorize, complete the square on x squared minus 2x. X minus 1 squared minus 1. Again, this might be where you became unstuck, because you've got to be really careful with the double negatives. So we're going to get a plus 1 and a plus 15. So it's going to be plus 16. It's only asked us the value of A, so it's going to be A is 16. Be careful, it's not 14. Right, brilliant. Today we're going to look at completing the square as a method to solve quadratic equations. I've just left it like that though. And we're actually going to return to Mesopotamia to start with, and the Babylonians. So this is a typical kind of puzzle, from a Babylonian puzzle from 2000 BC. I've added the area of my square to 4 times its side, and it is 60. What is the side of my square? Babylonians would enjoy doing puzzles like this, and they just look at the positive answers. They ignored negative answers to quadratics. I don't know how much they had a awareness of what a quadratic was. I presume they know that it had to be dealt with differently from, say, a linear equation. So let's set this up. I'm just going to remind you about this. You know, if we have a square and we want to find the side, then we can call it x and x. And then I'm adding to my square 4 times its side. So that's going to be 4x. And I could add this little bit on, 4x. And that is equal to 60 overall. So let's get away from the geometry problem. We have dealt with that. Essentially, we're trying to solve x squared plus 4x equals 60. This is our modern algebraic notation. And this is how we can do it. We can complete the square just like we did previously. It's going to be x plus 2 squared minus 4 equals 60. But this time I'm not interested in finding the turning point of a function. I've actually got an equation to solve. And this is what I can do. Because I've managed to complete the square, I've suddenly, instead of having a term in x here and a term in x here, I've got a single term with x in. And I can actually add 4 to both sides to make it 64. This is brilliant because now I've got something squared equals 64. I can take the square root. So it's going to be x plus 2 equals the square root of 64. Now the Babylonians would have done this and not included the negative, but we actually have to remember that when we take a square root, we need to include plus or minus. So it's going to become x plus 2 equals plus or minus 8. If we include plus 8, x is 6. If it's minus 8, it's going to be minus 10. So the Babylonian, okay, in our situation, it's just going to be 6. That is going to be the side length, the side of my square, and we're done. For us, more generally, if we were just solving this equation here to start with, we would also include the minus 10. And essentially, this is how we can use completing the square to solve quadratics. And we're going to do that for the rest of this lesson. Because most quadratics cannot be factorized. We've looked a lot at factorizing. It's a great method. It's really useful in different situations, but it's not always going to work. Okay, it would have worked here actually. I'm not going to go into how, but often they won't. And instead, we'll get roots in third form. So they exist, but they're just not as pleasant as, say, 6. You might get root 3 plus 2 or something like that. And of course, we can also find a turning point in the line of symmetry by completing the square. And with these 3 things, we can sketch any quadratic. Previously, we've sketched quadratics using the roots, but now we've factorized using the roots, but now we might get thirds as the roots, but we could still find them here and here. We could get the turning point by completing the square, and we could get the line of symmetry. So really powerful method going on. All right, let's take a look at an example. I've done one already, but I'm going to jump straight into dealing with it with 2x squared minus 8x plus 1. It's going to be similar. It's going to be easier if you didn't have a 2 there. So previously, we've got completed square form as follows. I'm not going to go back through that. You've already accomplished this yourselves. So if I want to find the roots, what I need to do is essentially set it equal to 0. We call the roots where it intersects the x-axis. So it's going to be minus 7 equals 0. All right, and now we're going to do basically what we did before with the Babylonian problem. I'm gonna get it. So normally, often when we factorize quadratics, we try and get it equal to 0, but strangely enough, we're going to actually not do that now. We're going to get 7 over here by adding 7, and then we're going to divide through by 2. So I'm just going to get rid of that. I'm not going to write a whole other line down. Right, this is brilliant because now we can do the same as before. We can square root both sides. So it's going to be plus or minus the square root of 7 over 2. And actually, we're pretty much there. The answer is just x equals 2 plus or minus the square root of 7 over 2. I get a not particularly nice third as my answer, but that's it. You might just write down that x equals 2 plus root 7 over 2, or 2 minus root 7 over 2, if you wanted to write the answers separately. Whew, good. Good, good, good. Try this one yourselves. So for this one, I'm finding the roots. So again, I'm going to set this thing equal to 0. I'm going to add 2 to both sides, and then I'm going to divide 3 by 3. So it's going to become 2/3. So we've done the main bit. Now we're going to take the square root of both sides. So it's going to be the square root of 2/3, but it's plus or minus again. So x equals 2 plus the square root of 2/3, or 2 minus square root of 2/3. Really quick, really great method, as you can see. Obviously, we started from completing square form, so that's why it's a bit quicker than it would have been otherwise. And I'd like to try these with negatives in as well. So for this one, I'm going to set this equal to 0, and then actually I'm going to make it so it's x minus 1 squared equals minus 3. Now, in this case, when we take a square root, we're trying to take square root of a negative, and that is not going to be possible. We'd get x minus 1 equals plus or minus the square roots. So this is not allowed. Actually, we say no real solutions. In A-level maths, we always talk about the real numbers, the numbers on the number line. And so we're not allowed to have things that are not on the number line, but they do exist. So we say no real solutions in this case. If we just look at the sketch, then we'd see it's an unhappy quadratic. We get a turning point of minus 3 when x is 1. So it's going to be sort of down here, and it's going to look like this. We would have seen that previously. There are no roots. Okay, it's worth talking about that one. This one here. Similar starting point. Plus 15 equals 0. This time, though, it's going to be x minus 3 squared equals 15, because I can add that to both sides, and we do get some solutions. Brilliant. So we can take the square root and we're going to get x is equal to 3 plus root 15, or 3 minus root 15. Nice. Again, third answers, but that's okay. If we put it in the quadratic formula, we would get the same thing. And remember, it doesn't factorize nicely. The factorization, in fact, is going to be x minus 3 minus root 15, and then x minus 3 plus root 15. And basically, if I have a factorized form, I just take the negative to get, well, actually, that's not quite right. I'd have to put a minus in front of that as well, but I'm pretty much there with it. Basically, what I'm trying to say is if you get solutions of 1 and 2, you get the quadratic, it would be x minus 1, x minus 2. So if I get the solutions 3 plus root 15 and 3 minus root 15, it's the same idea. I get this. I just need to make sure actually when it's factorized, I'm going to get a minus x squared out of it at the end. So I do have to stick a minus there because multiple quadratics have the same solution. Don't stress too much about that. I just threw that in at the end, to be honest. We're nearly at the end, but here's one more for you. So the general quadratic, previously we showed that you could write it in completed square form like this. I'm not going to recap that right now. can you take that and try and find the roots? X equals something, it's going to be in terms of A, B, and C. So I'm going to talk through this one. I'm just going to start from up here. We're going to set it equal to 0 for the roots. And then I'm going to add b squared over 4a and minus c from both sides. Okay, I'm then going to write this over a common denominator. So it's going to become b squared minus 4ac all over 4a. I've essentially times this by 4a and divided it by 4a and then brought the fractions together. And then I'm going to divide through by a, because before I take the square root, I want to do that. And that is equivalent to putting a little a squared there. When I divide by a, I can just put it on the bottom. And now I take the square root. It's going to be x plus, let's try that plus again, b over 2a. It's going to equal the square root of this. Plus or minus. Now we can actually use our knowledge of surds and write this as a square root over b squared minus 4ac divided by the square root of 4a squared. But that simply becomes 2a. I've done that quite quickly, but I'm hoping that's all right. And then I'm going to minus b over 2a from both sides, so it's going to become minus b over 2a. But the thing is, I can put it all over 2a, and I get this as my final answer. That's one way of writing it. Anyway, arguably the most simple. So we can use completing the square to derive a general formula for solving any quadratic, and you've probably seen this before. This is known as the quadratic formula. Now, if you struggled with that, don't stress. I'd say, hopefully it roughly makes sense. And it is the most general thing. So if you understand this and you can apply it, then you can apply completing the square to any quadratic. That's the main thing. This is non-examinable. You won't be asked to derive this in an A-level exam. Having said that, I'd say it's absolutely essential for an A-level student to see it, because this formula seemingly comes from nowhere when you first discover it, and we're going to be studying this formula a little bit more, but it simply comes from, I say simply, it comes from completing the square on the general quadratic and then solving it from there on. So my final challenge, if you're up for it, is can you, if you didn't quite get there especially, can you start from the general quadratic? Here we go. Can you complete the square on it, set it equal to 0, and then get to the quadratic formula? It's good. It's worth trying to learn how to do that and understand it. It just shows that your algebra is pretty spot on and your completing the square is pretty spot on. Otherwise, I'm going to get you to do some more practice, so head on over and do some of that. Thanks.